I'm assuming everyone has looked over the lab exercise. Remember, this is not a full lab. You do not have to write a lab report like you do for the rotational inertia one. Just a lab exercise, just fill in the blanks. Take some measurements, fill in the blanks. And the idea is we are going to explore whether in fact it is true that for an object in static equilibrium, the sum of the forces and the sum of the torques on that object is zero, are zero. Right, that's our condition for static equilibrium. Sum of the forces equals zero, sum of the torques equals zero. And we are going to do two different versions of that, okay? In the first version, right, we're going to take our iOLab. I hung my iOLab from a string, okay? Let's put it this way. And I'm going to hang it from this rod. I attach the string to this little ring in the top of the iOLab. I put another string loop on the force sensor, to which I attach the eye bolt here, right, the eye bolt, okay? And I'm going to take a ruler. In this case, it's a meter stick, but you don't have to use a meter stick. You can use any rod or stick or ruler whose length you can measure, okay? And I'm going to take an object. In this case, I have a nice actual physics weight, but you can use anything you want. You can use an old gym shoe or I don't care what, anything. Actually, don't use an old gym shoe. That's too heavy. Try to keep it under about 50 grams, okay? And I'm going to hang that object. You guys see I can't see what I'm showing you, but can you guys see my meter stick hanging from the iOLab and the mass hanging from the meter stick, right? And then all you got to do is, of course, adjust the positions of the objects until it's in static equilibrium, until the meter stick is balanced. Okay, somewhere right around there. Okay, my meter stick's wobbling, but you get the idea, okay? You're going to use the iOLab software to measure the force the iOLab feels, okay? You're going to measure the mass of the meter stick using the iOLab. You're going to measure the mass of your object using the iOLab. And you're going to measure the position of the object on the stick and the position of the iOLab on the stick. And you're going to measure both of those positions from one or the other end of the stick. Okay, in other words, I'm going to choose my axis of rotation to measure torques to be either this end or this end of the stick. It doesn't matter which end you choose, but you have to make all the measurements from that end. So in this case, since, if you can see, my meter stick has its zero on this side. So just to make life easier, I'm going to use this as my origin. And the force measured by the iOLab when both are hanging in equilibrium, I can then calculate the sum of the forces and the sum of the torques. And the torques will be measured about this axis, right? So how many torques are acting on this stick right now? It's in equilibrium, I got not quite there, but right about, getting these things to balance is a real pain, so right about there. How many torques are acting on this stick right now? Ignore the fact that my hand is touching the stick. How many torques? Or how many forces are acting on the stick? 1, 2, 3, 4, 5, how many? Anybody? Well, identify one of the forces acting on this stick right now. What's the easiest one?
The weight of the meter stick.
The weight of the stick. The stick has a weight, right? And that force is acting at the center of mass of the stick. which in this case is right at the 50 centimeter point, assuming this stick is uniform, right? Okay, so I have a weight of the stick acting right there at 50 centimeters. That's one force. What else?
The string connecting it to the iOLab?
Yeah, the string connected to the iOLab, right? The iOLab is pulling up on this stick with a force equal to whatever the iOLab reads, right? 3 newtons, 2 newtons, 1.5 newtons, whatever it is. You're going to read that right from the iOLab software. Okay, that's 2 forces. What's the third one? Oops, I gave it away. Sorry, there's 3 of them. What's the third one?
The force of the string connecting it to the weight.
Yeah, this weight here is pulling downwards with whatever its weight is. You've measured that with the iOLab, of course, right? So I have a force downward from this weight, a force downward from the mass or weight of the stick itself, and a force upwards from the iOLab. And let's see if the sum of those 3 forces is 0, and the sum of those 3 torques, as measured about this end of the stick, are 0. So you're going to calculate the sum of the forces up and down, calculate the sum of the torques clockwise and counterclockwise, negative and positive, and see if they are the same or they add up to 0. No problem. Okay, any questions about that? By the way, you don't have to use a big old meter stick. You can just use a ruler, whatever you have. You don't even have to use a ruler. Use any uniform stick whose length and mass you can measure. Okay? You don't want to use like a baseball bat or a sort of skateboard or something. Why not? Why would that be a bad idea?
It doesn't have a uniform mass.
Exactly. Finding the center of mass, which is the point where you are measuring its weight, finding the center of mass of a baseball bat is a tricky matter. But a uniform stick or rod, it's easy. The center of mass is in the center. Okay. Any questions about that first part of the lab? This is like, we're trying to quantify what you intuitively knew in first grade, right? That you can balance things by sticking them on a stick, and you're on the seesaw with your friends, and you put 2 people up close and 1 far away, and they balance out. You knew this back in 2nd grade, but now we're going to put numbers to it. Okay, so that is the first part. The second part, now what's the kind of easy aspect to this part of the experiment? Well, the easy thing here is that the forces are all in the y direction, right? The forces are all up and down. There are no x components of any force, as long as the meter stick, when it's in equilibrium, is horizontal, right? Then all the forces are vertical. That's easy. You don't even have to try to calculate any x components of forces. Okay, but the second part of the experiment is a little more complex, because what we're going to do is then, can you guys see my wall here? I can't see what you see, but do you guys see my little corner here with my stick on it? Yeah, okay. So what you're going to do now is hang your weight from the force sensor in the iOLab. You're going to take a stick, maybe a ruler, again, some uniform stick. You're going to wedge it into a corner of a wall or something, and then you're going to drape the string over the stick. Whoa. Gotta get it just right, okay? You're going to drape the string over the stick and hold it. So the iOLab and string are horizontal. Now, obviously, this is a source of error, because how do you know it's exactly horizontal? But do the best you can, okay? So the iOLab and force sensor and string are all in a horizontal line. The mass is hanging off the ruler, and the ruler, or stick, whatever you're using, is at an angle with respect to the horizontal, right? This angle theta here. And you have to measure this angle theta and the force from the force sensor. Okay, now measuring this angle might be a little tricky. In the lab write-up you see, I suggest taking a picture and then importing that picture into Tracker. And Tracker has an angle measuring icon you can press to measure angles. Or if you have like a protractor, you can try to just wedge the protractor in there and use that to measure the angle, okay? But somehow you're gonna have to measure this angle, okay? And there my ruler is in static equilibrium, okay? Now if the axis of rotation is the point down there where the ruler is wedged in the corner, how many torques are acting on that ruler about that axis of rotation? How many torques? How many forces are acting on the ruler? We got a bunch of forces here, right? There's some force from the wall pushing up on the ruler. There's a force from this weight pulling down. There's a force from the iOLab pulling this way. There's the weight of the ruler pushing down from its center of mass, right? But of those forces, which ones are exerting a torque about the axis of rotation where the ruler is wedged into the corner? Anybody? Think about it. How many torques are acting on this ruler right now about that axis down at the bottom? The answer is 3. But what are they? Anybody give me one?
The weight.
Sorry, Brandon, say it again.
It would be the torque from the weight, the iOLab, and the weight of the ruler.
Okay, so the weight of the ruler certainly exerts a torque, right? If this string wasn't here, look at that, it rotated. It felt a torque and it rotated downward. So there's a torque due to the weight of the ruler for sure. There's a torque due to the weight that's hanging down, R cross F. And there's a torque due to the force from the iOLab. Whoops. Only have 2 hands. R cross F. 3 torques. Weight of the ruler, force from the hanging weight, force from the iOLab. You can measure the force with the iOLab. You know the force exerted by this weight because you've already measured its mass. You know the force exerted by the ruler because you measured its mass. Now all you have to do is calculate those 3 torques. Okay? 2 positive, 1 negative. And again, see if the positive torques and the negative torques are the same, as they should be for an object in static equilibrium. Okay, does that make sense? 2 static equilibriums. 1, a rod hanging horizontally, and 2, a rod wedged into a corner at some angle. Your job is to calculate the positive and negative torques and positive and negative forces in both cases, and see if the positive torques equal the negative torques, the positive forces equal the negative forces. Okay? What do you guys think? Now this second one, there's a question I ask at the end. I say, I can't actually calculate the positive and negative forces on this angled stick. Why not? I could calculate the positive and negative torques about this point down here, but I cannot calculate the positive and negative forces on this stick. Why not? What information am I lacking that would allow me to measure the positive and negative forces on this stick? Hint, hint, hint.
Force of the wall.
Yeah, the force that the wall and the floor exert on the stick. I don't have any way of measuring that. I don't have a little force sensor between the stick and the floor, so I have no idea what force the floor and wall exert on the stick. We could put some kind of little force sensor between this and the floor, I guess. But we don't have that. But we can calculate the torques. How can we do that if we don't know the forces that the wall and the floor exert on the stick? How are we able to then calculate the torques? Hint, hint, hint.
Radius at that point, since it's the axis of rotation is 0. So it's
Exactly. Because the forces from the wall and the floor exert no torque about the axis of rotation, because they are acting right on the axis of rotation. So who cares what those forces are? They don't even enter into the torque equation. Whew. Of course, if we chose this point, the top end of the stick is our axis of rotation, then we'd be screwed, because then we would have to know those forces down there to calculate the torque. But we're not that dumb. We're going to choose the point where those forces are applied down the corner to calculate torques, to make sure that those torques down there disappear. Okay? What do you think? Doable? Like every other lab we've done this semester, really, taking the data should take you 5 minutes. Analyzing the data might take you a few hours. Okay? Actually, this one is tricky. If you use a meter stick, let me tell you, it's really tricky to get this to stay balanced horizontally, because the tiniest change in the position, and this thing goes like this. So, do the best you can. If your stick is starting to move a little, just gently use your finger to stop it. Don't exert a force, or don't exert much force, but, meter sticks are a lot harder. Use any stick you want. Okay, that should be enough to get you started. So next Friday is going to be our last lab, okay? I don't know yet. It's probably going to be some kind of fluid thing, and I think what I'm going to do is make it, I don't want to say optional because then no one will do it, but I'm going to allow you to replace any other missing lab score with the one from next week, okay? We're going to try to probably measure the density of a fluid using the buoyant force. Okay, so just keep that in mind, but that'll be our last lab, okay? All right, any other questions or complaints? Oh yeah, I have pictures in there. You can see my pictures in the lab. Right up, right? Yeah. By the way, this is my trick for making a nice little mass. It's just get a little baggie and put some rice in it. Makes for a nice little mass. And you can adjust it to be large, small, whatever you want. Okay. Anything else before I let you guys go? Have a good weekend. Do some physics problems. No? Okay, we will see everyone on, what's this? Something in the chat? Oh, okay. Okay, yeah, we'll see everyone on Monday. We'll have our usual quiz, some gravitational questions, maybe a little static equilibrium question or two, and then we will move on quickly to fluids. We're going to have to really rocket through fluids here, but we'll figure it out. Okay, have a good weekend. We'll see everybody on Monday.